In this class, we are going to discuss Cmos logic. Cmos means complementary metal oxide semiconductor. The digital circuits we have discussed so far consist of bipolar junction transistors. To integrate more complex circuits within small space and to reduce the power consumption, Mosfet transistors are preferred rather than bipolar junction transistors. The important characteristics of CMOS circuits are switching speed is very high, fan out also very high, noise margin also appreciable. The CMOS transistors are basically classified into two types. Number one, P-channel MOSFET or Pmos, N-channel MOSFET or Nmos. The both transistors are operated in two types of modes of operation. Number one, depletion mode. Number two, enhancement mode. Before discussing these CMOS logic circuits, let us see what are the construction detail, how it is working of MOSFET transistor. So in this case, we select N-channel MOSFET or NMOS or N-channel MOSFET. The N-channel MOSFET consists of a lightly doped semiconductor bar. This is the lightly doped P-type semiconductor bar. P-type semiconductor bar. Two heavily doped N-type materials are diffused inside of this bar. This is the one region, this is another region. This region is heavily doped N-type materials. This is the N region, N plus, this also N plus. N plus stands for more density. The impurity density is high. This above this bar develop a layer of silicon dioxide. This silicon dioxide layer is known as a insulating layer. Now, make small opening above this region. Through this, insert one lead. This lead is known as source terminal. Source terminal. Similarly, make small opening near this region. Through this region, take one more lead. This is known as drain terminal, drain. The source is similar to emitter of the transistor and drain is similar to collector of the transistor. The region in between the source and the drain is called the channel region. The channel region is lightly doped N-type material. This is the lightly doped N-type material. This region is known as channel region. Above the channel region made a aluminum coating or you form a thin layer of aluminum. From this aluminum layer, take one more lead. This is known as gate. This is aluminum. Therefore, this MOSFET, N-channel MOSFET transistor consists of three terminals, namely source terminal, drain terminal and gate terminal. The beauty of this construction is the region, the central channel region, this region is acting as a parallel plate capacitance. How parallel plate capacitors. The parallel plate capacitor consists of two parallel plates. In between the two parallel plates, there is a medium, insulating medium. That medium is known as dielectric medium. When positive charges are deposited on one side of the plate, the equal negative charges are induced on the opposite side of the plate. This is the concept for parallel plate capacitors. The same concept used in the MOSFET transistor. Here, the gate terminal is acting as a one plate of this capacitor. The central region, this is called the SiO2 layer. SiO2 layer. This is the insulating layer. The purpose of this layer is to prevent entering of outside impurity within this semiconductor bar. This is the insulating layer. This insulating layer is acting as a dielectric medium. Then channel region. This channel region is acting as another plate of the parallel plate capacitor. Therefore, this structure consists of one parallel plate, this is another parallel plate. In between these two parallel plates, there is a dielectric medium. The dielectric medium is acting as a SiO2 layer, silicon dioxide layer. This is the construction details of N-channel MOSFET. Now, biasing of this transistor. The source is always given to negative of the power supply. The positive is given to drain terminal. This is given to drain terminal. The gate is operated in both mode, that is enhancement mode and depletion mode. You can operate both negative voltage and positive voltage. First, let us consider this gate is operated with negative voltage with respect to source. This VGS, the voltage between gate and source, and this is a voltage between source and drain. So, this voltage is equal to VDS, drain and source voltage. Now, how this MOSFET, N-channel MOSFET is working? Through this source terminal, the majority carriers are enter into the channel. Through this drain terminal, the majority carriers are leave from the channel region. Now, the negative polarity is given to cathode terminal. Because of negative charges, the equal and opposite charges induced in the channel region, that is the positive charges are induced. Already the channel region is made up of N-type material. It is a lightly doped N-type material. Now, because of application of negative voltage at the gate terminal, the positive charges are induced. This forms a depletion layer. This is called as a depletion region, depletion layer. This depletion layer adjusting control the width of channel region. When the magnitude of the negative voltage at the gate terminal increases, more number of positive charges induced and the width of the depletion region is gradually increasing. Therefore, it controls the charge carrier move from source to drain terminal. At the same time, the current flow from drain to source terminal they are also controlled. Therefore, the drain current is controlled with the help of this gate voltage. When the negative voltage at the gate terminal increased, the positive charges increased, depletion region increased, current will be decreased. So, the current will be decreasing means the current will be depleted. This type of a mode of operation is known as depletion mode of N-channel MOSFET. The other mode of operation, instead of this negative voltage, you connect positive voltage to the gate terminal. Because of these positive charges, now the negative charges are induced. Already the channel region is made up of N type of materials. By introduction of positive charges on the gate terminal, more number of negative charges are induced in the channel region. Therefore, the density of negative charges in the channel region increasing, otherwise the conductivity of the channel region will be increasing. Therefore, more current flow from drain to source terminal. The current will be enhanced. The flow of current will be enhanced. Therefore, this mode of operation is known as enhancement mode of operations. This is the operation details of N-channel MOSFET. In the case of P-channel MOSFET, the same argument hold good, but only thing is the P-type semiconductor body is made up of N-type semiconductor bar, and the source and the drain regions are made up of P-type semiconductor bar, and the channel there is the P-channel. Therefore, it is called the P-channel MOSFETs. Now, let us compare Pmos transistor and NMOS transistor with Pnp transistor and NPN transistor. First, let us see N-channel MOSFET. The MOSFET transistor consists of 3 electrodes, namely gate, source, drain. This is drain terminal, this is substrate, this is source terminal. Usually, the substrate and the source are interconnected. This is connected to ground terminal. The drain is given to positive of the power supply VDD. This is gate terminal. The gate is insulated from source and the drain and also substrate. Therefore, the gate is separated by the small gap here. This is NMOS transistor, N-channel metal oxide semiconductor field effect transistor. In the case of NMOS transistor, the arrow is moving towards the gate terminal. This is the circuit symbol for NMOS transistor. Similarly, for NPN transistor, this is the base terminal, the collector terminal, this is the emitter terminal. The emitter terminal is grounded, collector terminal is connected to positive of the power supply VCC. This is base terminal. This is the base emitter, this is the collector. But in the case of NPN transistor, the arrow is moving from base terminal to ground. Arrow. See here, the arrow, compare the arrow of both transistors. In the case of NMOS transistor, the arrow is moving towards the gate terminal, but in the case of NPN transistor, the arrow is moving away from the base terminal, which means that the current flow here is from base to emitter terminal. This is the reason. Similarly, we have to discuss Pmos and the Pnp transistor. For Pmos transistor, again you put 3 short lines. This is substrate, this one is the source, this is drain terminal, this is gate terminal, gate, this is a substrate, this is the source, substrate, drain, and here also this is a drain, this is substrate, this is source. Here the substrate and the source are usually interconnected. This terminal is connected to positive of the power supply VDD. Drain terminal is grounded here. This is Pmos transistor. What is the direction of arrow? The direction of arrow is quite opposite to Nmos. In the case of Nmos, the arrow is moving towards the gate. In the case of Pmos, the arrow is moving away from the gate terminal. This is the direction. Then Pnp transistor, base, collector, emitter. The collector of Pnp transistor is always connected to negative of the power supply. This is minus VCC. The emitter, Pnp transistor, the arrow is moving inside. The emitter is connected to positive of the power supply. In the case of Pnp transistor, this is Pnp transistor is the emitter terminal, this one is the base terminal, this one is the collector terminal. This shows the base terminal. This is Pnp transistor. So just you compare the circuit symbols of Nmos transistor with NPN transistor and Pmos transistor with the Pnp transistor. You can understand that the direction of the arrow is quite opposite to the Nmos and the NPN transistor. Similarly, the direction of the arrow is opposite in the case of Pmos and the Pnp transistor. Now, how it is conducting, that is very important. The input voltage to the gate is, you say, Vi. The input here also Vi. The input here also Vi. Here also the input is Vi. Depends upon the input voltage, the mass and the transistor, bipolar junction transistors decides that operations. When Vi is equal to 0, input is 0, the Nmos transistor and NPN transistor both are off condition. When Vi is equal to 1, both Nmos and NPN are on condition. This is a very important condition you keep in memory while discussing any CMOS circuits. Similarly, when Vi is equal to 0, the Pmos and Pnp transistor became on. When Vi is equal to 1, Pmos and Pnp transistor is in the off condition. This is a very important operation of MOS and bipolar junction transistor. Now, let us discuss one of the important CMOS gate called as Cmos inverter. Already I told you that Cmos means complementary metal oxide semiconductor. Why the name complementary? The same circuit consists of both Nmos transistor and the Pmos transistor. The both transistors are complement to each other. Therefore, the name is called as complementary. Let us see what is the circuit diagram for CMOS inverter, how it is working. In this case, you take two transistors. One is the Pmos transistor, other one is the Nmos transistor. This is Pmos transistor, and this is NMOS transistor. This is gate terminal, this also gate terminal. The both gate terminals are interconnected. Across this interconnection, apply the input voltage capital A. The drain terminal of this transistor is PMOS transistor. The lower one is the NMOS transistor. The source and the substrate of both PMOS transistors are interconnected. In the case of PMOS transistor, the arrow is moving away from the gate terminal. That indicate this. And this is connected to positive of the power supply plus VDD. This is a drain terminal. This one is substrate. This is source terminal. This one is the drain terminal. In the lower case, this is a drain terminal, this is substrate, this is source. The source and the substrate both are interconnected. This is substrate, this is source S, this is a drain D. The both drain terminals are interconnected. Through this interconnection, take output voltage capital Y. This source terminal is given to negative of the power supply, otherwise it is grounded. The input is given to both gates of PMOS and NMOS transistor. In the case of PMOS transistor, the arrow is moving away from the gate. In the case of NMOS transistor, the arrow is moving towards the gate terminal. So here the arrow is moving towards the gate terminal. The construction detail is over. Here they have to measure output voltage between the common drain terminal of both PMOS and NMOS. So this circuit consists of both PMOS and NMOS transistor. Then it is said to be complementary metal oxide inverter. We know that the truth table of NOT gate, A output Y is equal to A bar. When A is equal to 0, the output is complement of input, you get 1. When A is equal to 1, the output is equal to 0. This is the truth table for NOT gate. Now let us analyze this truth table with the help of this circuit. First, let us take the first row of the truth table. A is 0. The A is equal to 0. Already I told that when input voltage is 0, PMOS switched on, NMOS switched off. When the input voltage is 1, PMOS off condition, NMOS on condition. Keep in memory this. Now A is equal to 0. PMOS transistor switched on. NMOS transistor, it is switched off. It is acting as a open switch. PMOS transistor is acting as a closed switch. Therefore, there is a break here, because since the NMOS transistor now acting as a open switch, there will be break. The applied positive voltage passes through the NMOS transistor and it exists at the point capital Y. It cannot pass through the ground since this is acting as a open circuit. When you measure voltage between this output terminal with respect to ground, it shows high value. That is the first row of the truth table. In the second case, A is equal to 1. Apply A is equal to 1 here. High voltage. When A is equal to 1, the input is high to the PMOS transistor. Definitely the PMOS transistor is in the off state. It is acting as a open circuit. Now this is became off. This circuit will on. The lower NMOS transistor switched on, but The drain is connected to positive of the drain terminal through this transistor, Pmos transistor. Since that Pmos transistor is acting as a open circuit, there is no link between the drain terminal and the positive of the power supply. Therefore, the output this also in the off condition, the output across this Y terminal is equal to 0. That shows the second line of the truth table. When high input is given to the input of this inverter gate, you get low output. When low output is given to input of the inverter gate, you get high output. This is the operation of Cmos inverter. The another Cmos circuit is Cmos NAND circuit. The Cmos NAND circuit consists of 4 MOS transistors, in which the 2 MOS transistors are Pmos transistor. The another 2 MOS transistors are NMOS transistors. Now let us see what is the diagram for Cmos NAND gate. This is both are Pmos transistor is a gate terminal. This also gate terminal. This is substrate. This is source. Both are interconnected. Here also the substrate and the source are interconnected. This is drain terminal. This also drain terminal. You say this is transistor T1. This is transistor T2. These both transistors are Pmos transistor. These Pmos transistors are acting as a load transistor. In the case of Pmos transistor, the arrow in the substrate is moving away from the gate terminal, and here also moving away from the gate terminals. The both, this is drain, this is source 1, this is drain 1, this is source 2, drain 2. The both source 1, source 2 are interconnected, which is connected to the positive of the power supply. So these two are interconnected, and this is connected to positive of the power supply plus VDD. These both transistors are Pmos transistor. The Pmos transistor now it is acting as a load. Now apart from these two Pmos transistors, take two NMOS transistors. These are two NMOS transistor, is a gate terminal. This is also a gate terminal. You say this transistor is T1, this transistor is T2, and this transistor is T3, and this transistor is T4. These both are belongs to NMOS transistor. This is substrate terminal, this is source terminal, both are interconnected, which is grounded. This is substrate. In the case of NMOS transistor, the arrow is moving towards the gate terminal. Arrow is moving towards the gate terminal. This is drain terminal, and here also this is substrate, this is source. The arrow is moving towards the gate terminal in the case of NMOS transistor, and both are interconnected. This interconnection is given to this drain terminal. This is drain 2 is over, and here also this is drain 3, and this is source 3, drain 4, source 4, and this both are interconnected here, and this drain 1, drain 2 both are interconnected here. So across this point you measure output voltage with respect to ground. This is output voltage. And then there is an interconnection between the gate terminals are there. This is A, this is B. Sorry, this is A. Let us see which one is the B. Transistor T1 and the transistor T3 both are interconnected. The gate terminal of the transistor T1, gate terminal of the transistor T3 both are interconnected. So these two terminals are interconnected. Similarly, the transistor gate terminal of transistor T2, gate terminal of transistor T4 both are interconnected. Here both are interconnected. Through this you take one terminal, this terminal is capital B. The inputs are capital A, capital B. The outputs are measured between the terminal capital Y with respect to ground. Transistor T1, transistor T2, both transistors are Pmos transistor. These transistors are acting as a load. The lower two transistors, the NMOS transistor, both are belongs to NMOS transistor. This is acting as a driver transistor. This is in the serial form, this is in the parallel form. The Pmos transistors are in the parallel form, the NMOS transistors are in serial form. This is a cascading one over another. The gate of T1 and the gate of T3 are interconnected. Similarly, the gate of T4 and the gate of T2 are interconnected. So the construction details of this transistor is over. Now let's see truth table. A input, B is another input. The output Y is equal to A dot B in the case of NAND. When A is equal to 0, B is equal to 0, A is equal to 0, B is equal to 1, A is equal to 1, B is equal to 0, A is equal to 1, B is equal to 1. The output conditions are 0, 0 equal to 0, 0 bar is equal to 1, and 0 into 1 is equal to 0, 0 bar is equal to 1, 1 into 0 is equal to 0, 0 bar is equal to again 1, 1 into 1 is equal to 1, 1 bar is equal to 0. This shows the truth table for two input NAND gate. And you have to construct one more truth table to study the operation of this CMOS NAND gate. That is A, input A, input B, transistor T1, transistor T1, transistor T2, then transistor T3, transistor T4, the output Y. The A transistor values 0, 0, 0, 1, 1, 0, 1, 1. The T1, T2 both are Pmos. These both transistors are Pmos. T3 and T4, these both transistors are NMOS transistor. Now A is equal to 0, B is equal to 0. The input A is equal to 0, input B is equal to 0. T1, T2 both are Pmos transistor. When the input to the Pmos transistor is 0, it is switched on. T1 is on, T2 also on. T3 and T4, for the input A and B, NMOS transistors are off condition. The input is 0, the NMOS transistor is 0. So this is 0 and this also, the 0 means this is off. This is off condition, this is also off condition. The second case, A is equal to 0, B is equal to 1. A is equal to 0 means the 0 signal is connected to T1 and the 0 signal is connected to T3 of NMOS transistor. The 0 signal A is connected to T1, definitely T1 on. The same 0 signal connected to T3. This is the NMOS transistor. So T3 is off condition. Now you come to B signal. The B signal is here. The B signal is here 1. The 1 signal is connected to T4. This is the NMOS transistor. It switched on. T4 on. The same 1 signal is given to T2. T2 is Pmos. When the input to the Pmos is 1, it is off condition. This is off condition. Similarly, 1, 0. The A signal is now 1. This is equal to 1. B signal is equal to 0. B signal is equal to 0. The A signal now connected to T1. T1 is the Pmos. It is definitely off. T1 is off. The same A signal connected to T3. T3 is Nmos. It switched on. T3 on. T3 became on. What about B signal? B signal is 0. The 0 is connected to T4. T4 is the Nmos. Definitely it is in the off condition. T4 is off condition. The B signal is equal to 0. The 0 is connected to T2. T2 is the Pmos. It switched on. T2 on. The last case. A is equal to 1, B is equal to 1. 1 means Pmos definitely 0. 1 means Nmos definitely switched on. So here A is equal to 1, B is equal to 1. This A is equal to 1 connected to T1 and also T3. T1 became off and T3 became on. T1 off and T3 Nmos this became on. Similarly, the B signal is 1 here. The 1 is connected to Nmos, T4 Nmos, this is on. T4 on. And same B signal, 1 is connected to T2, T2 is the Pmos, it is off condition. This is the off condition. This is the another operating table of CMOS NAND gate. So far we have seen for the signal, depending upon the signal A and B, which transistor on and which transistor is off, that shows in this table. Now let us analyze the output. You get output only when any one of the transistor T1 or T2 is on, because it is connected in the parallel form. If any one of the transistor T1 or T2 switched on, you get output. Otherwise, we don't get any output. In the first case, T1, T2 both are on. Definitely you have output. How this output? These both are on. It is acting as a closed circuit. The both transistor T1 and T2 is acting as a closed circuit. The applied voltage plus VDD, this is passes through the transistor T1 and T2 and it exists at the point capital Y. So the output is equal to Y, it is the high. Output is high. Second case, A is equal to 0, B is equal to 1. So in this case, T1 is on, T2 is off. But anyway, if any one of the transistor is switched on, it is acting as a closed circuit. Through the closed circuit, the output, the supply voltage plus VDD passes through output terminal. Therefore, in this case, T1 switched on, it is acting as a closed switch. Through this closed switch, the applied bias plus VDD is passes to output terminal. So again, the output is equal to high. This shows the first row of the two table, second row of the two table. The third case, A is equal to 1, B is equal to 0. In this case, A is equal to 1 and B is equal to 0. Look here, when A is equal to 1, this is definitely off. The input to the Pmos transistor is high, definitely this transistor is off. B is equal to 0. B is equal to 0. This 0 is connected to T2 Pmos transistor. When the input to the Pmos transistor is 0, definitely this switched on. T2 switched on. This is acting as a closed switch. Through the closed switch, the applied plus VDD is passed through the closed switch and it exists at the point Y. Therefore, the output also again high. High. This shows the third row of the truth table. The last row of the truth table, 1, 1. A is 1, B is 1. So in this case, A is 1 means this is directly given to the PMOS transistor T1, P is 1, this also connected to the gate of PMOS transistor 2, T2. Both gate inputs are high. High means it is switched off. Switched off means the both transistors are acting as a open circuit. There is no possibility to move this plus VDD voltage to the output terminal. Therefore, definitely the output in this case is low. That shows the last row of the truth table. This is the operation details of CMOS NAND gate. The another important gate is CMOS NOR gate. Now let's see what is the circuit diagram for CMOS NOR. As we have seen in the CMOS NAND gate, here also 4 MOS transistors are used. The 2 MOS transistors are PMOS transistor, the another 2 MOS transistors are NMOS transistors. Whereas in the case of NAND, CMOS NAND, the PMOS transistors are in the parallel form and the NMOS transistors are in serial form. But in the case of CMOS NOR gate, the PMOS transistors are in cascaded form, serial form, and the NMOS transistors are in the parallel form. Let's see what is the circuit. This is a PMOS source, substrate, drain, gate, then source, substrate, drain. The substrate and the source are interconnected here. This is the drain terminal, this is source 1, this is drain 1, this is source 2, this is source 2, S2 and drain 1 both are interconnected. This is substrate, this one is drain terminal, drain 2, this is a substrate, this is the gate. These both transistors are belongs to PMOS transistors. This is PMOS transistor. This is acting as a load. The PMOS is acting as a load transistors. In the case of PMOS transistor, the arrow is moving away from the gate. So away from the gate, and here also away from the gate. This substrate and this substrate both are interconnected here. This source is given to positive of the power supply plus VDD. This is transistor T1, this is transistor T2, is the gate 2, this is the gate 1. These two transistors are in the cascaded form, serial form. The PMOS transistors are in the serial form in the case of CMOS NOR gate. Now let's see how the construction for NMOS transistor. This is 3 terminals of NMOS. This is the gate terminal, this is substrate, this is drain terminal, this is source terminal. The substrate and the source are interconnected. This is the gate, this is the drain. This transistor is T3. Therefore, the source is S3 and the drain is equal to D3. Similarly, one more gate, NMOS gate. It has 3 terminals. This is the gate terminal. The substrate and the source both are interconnected. Since these 2 transistors are NMOS, in the case of NMOS, the arrow is moving towards the gate terminal, in this substrate terminal, towards the gate terminal. This is a drain terminal, this is transistor T4, this terminal is drain 4, this is the source 4. The source 4 and the source 3 both are interconnected. This interconnection is given to the ground. Now the drain 3 and the drain 4 both are interconnected. This interconnection is given to this drain 2, T1 and T2. Further, the T1 and T3 are interconnected. So this T1 and this T3 both are interconnected. Similarly, the T2 and T4 are interconnected. T2 and T4 are interconnected. The dot only the connection, just crossing it is not a connection in the case of electronic circuit. Whereas in the case of electrical circuit, just crossing is the connection. That is the difference between electrical and electronic circuits. Say you give input A and input B to this circuit. This circuit is called as Cmos NOR gate. Now, let us draw the truth table for two input NOR gate. A is the one input, B is the another input. The output Y is equal to A plus B bar. Is the usual truth table. A is equal to 0, B is equal to 0, A is equal to 0, B is equal to 1, A is equal to 1, B is equal to 0, A is equal to 1, B is equal to 1. These are the four possible input combinations. When A is equal to 0, B is equal to 0, 0 plus 0 is equal to 0 bar is equal to 1. The output is equal to 1. 0 plus 1 is equal to 1, 1 bar is equal to 0. 1 plus 0 is equal to 1, 1 bar is equal to 0, again 1 plus 1 is equal to 1, 1 bar is equal to 0. This is the truth table for two input NOR gate. Now let us see what is a working truth table for CMOS NOR as we seen in the case of CMOS NOR gate. Again A is the input, B is the another input, transistor T1, transistor T2, both Pmos transistor, transistor T3, transistor T4, both are NMOS transistors. The output Y, output is equal to Y. This is the working truth table for CMOS NOR gate. The different combination 0, 0, 0, 1, 1, 0, 1, 1. Okay, come to this circuit. This CMOS NOR gate consists of 4 transistors, namely 2 Pmos transistors. These 2 Pmos transistors acting as a load, and lower 2 NMOS transistor, this is acting as a driver transistor. The driver transistors are in parallel form, the load transistors are in serial form. This is quite opposite to the CMOS NAND gate. Now the first input condition A is equal to 0, B is equal to 0, which means A is equal to 0, B is equal to 0. Already I told that when the input to the Pmos is equal to 0, switch it on. When the input to the NMOS is equal to 0, it is switched off. See here, when A is equal to 0, this is connected to this Pmos is switched off. The B also 0, the 0 also connected to this Pmos transistor, this also 0. The both transistor now is acting as a open circuit. So in this case, when both transistors are switched on, then only you get output. The output is measured across this common drain terminal. This is the output point. This is the Y. This is the output point. Output point. The common drain terminal of Pmos transistor, common drain terminal of NMOS transistor, you have to measure the output. So in this structure, when both transistors are switched on, then only you get output. If any one transistor, Pmos transistor is open condition, you don't get any output. This is a very important condition. Let us analyze this CMOS NOR gate. This CMOS NOR gate, both Pmos gates are in the serial form. The both NMOS gates are in the parallel form. When input to the Pmos gate is low, it is switched on. When the input to the Pmos Pmos gate is equal to 1. Now let us analyze this circuit. Let's see the first input combination, the first row of the truth table. A is equal to 0, B is equal to 0. A is equal to 0, B is equal to 0. Already we have seen that when input to the Pmos is 0, it is switched on. When input to the Nmos is 0, it is switched off. Here the both inputs A is equal to 0, B is equal to 0, the both inputs are connected to the input of Pmos transistor. Both transistors now switched on. This is switched on, this is also switched on. It is acting as a closed circuit. When it is a closed circuit, the applied voltage plus VDD is passing through the two switch. This also closed switch, this also closed switch, and the output voltage, this plus VDD voltage, it existing at the output of terminal. The Y is equal to high value. The plus VDD is directly passing to the Y point. Y is equal to high value. T1 is on now, T2 is on now. But in the case of T3 and T4, T3 and T4, the both inputs are 0, 0. Definitely it is off condition. T3 is off condition, T4 also off condition. The Y output is equal to high. This is the first line of the truth table that satisfies this truth table. A is 0, B is 0, output is equal to 1. The second row, A is equal to 0, B is equal to 1. A is equal to 0 and B is equal to 1. So in this case, the A0 switch on the transistor T1, B is 1, the high input, switch off the Pmos transistor, this is off condition. So in this construction, if any one transistor is open circuit, definitely the output is equal to 0. In this two combination, if any one transistor is open circuit, the output is 0. So in this case, this lower transistor is acting as a open circuit. For the combination A is equal to 0, B is equal to 1, T1 became on, T1 became on, T2 became off, T2 is off, T3 is connected to 0, definitely T3 is off, and T4 is connected to one input, it is on, but this positive power supply is not connected to plus VDD because since it is acting as an open circuit, again this also off. The output now is low value. The important condition is if any one transistor in the cascaded form is open circuit, you don't get any output. The third case, A is equal to 1, B is equal to 0. A is equal to 1, B is equal to 0. So under this case, A is equal to 1, T1 is definitely off, T1 is off. B is equal to 0, this is on, but the upper transistor is acting as a off condition. The source terminal is not connected to plus VDD because it is acting as a open, therefore this also T2 also off. When both transistors are off, there is no possibility to switch on the transistor T3 and T4 even though the inputs are present. So again this transistor T3 and T4 are off, you get finally low output. The last case, A is equal to 1, B is equal to 1, A is equal to 1, B is equal to 1. So under this case, the high signal switch off the transistor T1 Pmos, this high signal switch off the transistor T2 of Pmos, both T1, T2 off, T1 off, T2 off. Definitely when T1, T2 off, this both lower transistor, Nmos transistor also off, even though when the inputs are present, it won't conduct because it won't get positive power supply from VDD. Since these two are acting as a open, this also off and this also off, the output is equal to low. This is the operation work table of CMOS NOR gate. This satisfy with this truth table.